Isn't that right, Genesis?
Yep.
Wait for it to load. Alright, let's go ahead and let's go over it. So you had 1 through 6 on page 196. So number 1, give 3 properties of ionic compounds and 3 properties of molecular compounds. Alright, Chris, what do you got for ionic?
Soluble in water, aqueous, and crystalline solid.
What was that second one?
Aqueous.
Okay, that's just another name for water.
Okay, it's soluble, or no, it's a water substance.
Alright, so aqueous solutions is probably what you saw. What's special about aqueous solutions? Can they conduct electricity?
Yes.
Yes, they can. Alright, so molecular compounds. What do you have for that one?
Gases, liquids, and solids with volatile components. Insoluble in water and soluble in non-polar
Good job.
solvents.
What was your middle one?
Which one?
What was your middle one? I just couldn't hear it.
Insoluble in water.
There you go.
Alright,
Alright, number 2. What is the optic rule, and why might this principle be considered the driving force of all its elements to react to form chemical bonds? We've talked about this, and now your book finally decides to tell you. Alright, Ethan.
Try the question one more time, please.
What is the optic rule, and then why is it the driving force?
But the great stability is caused by the great stability caused by filled outer shell atoms will tend to react chemically as to achieve a noble gas electron configuration.
Good job. Alright, number 3. Define ionic bond. Chris.
Ions attracted to negative. Oh wait, yeah. Ions attracted to negative ions is ionic bonds.
Alright, so what type of ions are attracted to the negative ones?
Positives.
Positive. So the positive ions and the negative ions are attracted to each other. Alright, Quentin, define covalent bond.
Chemical bond that results from the pairing of valence electrons between atoms.
Good job. Number 5. Give 2 examples of a covalent network. Alright, Ethan.
2 examples of covalent networks is diamond and quartz.
Good job. Yeah, silicon carbide is another one your book gives. Graphite is one your book doesn't give, but that's also an example of one. Alright, number 6. What is a metallic bond? Alright, Chris.
The chemical that bonds metallic atoms together is metallic bonds.
So describe it.
I don't know. I should tell me what I wrote.
Alright, so it's asking you what is a metallic bond. So it wants you to describe it a little bit more instead of saying it's just the bond between metals. So kind of like covalent bond is characterized by the sharing of electrons. That's what it's asking more of. Alright, Quentin, what do you got?
Chemical bonds that bind atoms together in the middle.
Basically the same thing Chris said. Alright,
Process.
Ethan. Alright, so with metallic bonds, or most of the metals, do they want their electrons? No. So this is what. Now, does anyone remember what's the term for electrons that don't have a home, to where they're constantly getting shuffled around?
Homeless.
There's a better term to
Ether.
that, but yeah, basically. What?
Ether.
What did you say?
Ether.
No.
Electrons.
No.
Valence? No.
Alright, delocalized. We'll talk more about that today. But basically, they don't have a home. They're not local.
Immigrants?
So they're more like foster. Think of it
Democrats?
that way. To where, now again, I'm not making fun of foster kids, but it's the idea. Is just make sure you prep it since I'm being
Yeah, but
recorded.
that would be like that.
Since I'm making recorded, since I'm being recorded. So, but it's the idea of they get shuffled around because nobody wants them. None of the metals are being locked. They're not locked in this place. Alright,
Yes.
application. Write the Lewis structure of calcium and fluoride atoms. Alright, so first I'm just writing just the Lewis symbols for them. Alright, should be really straightforward. Chris.
F and 7 dots.
That's 1, 2, 3, 4, 5, 6, 7. Calcium, what do you got?
Ca 2 dots.
How many dots?
2 dots.
Alright, so that's the Lewis structure. B, if calcium fluoride atoms are allowed to react, what will the Lewis structures be for the resultant ions? Alright, Ethan?
I had Ca plus 2.
Good job, because that one gets rid of its electrons. Now fluorine will take how many?
Plus 4.
Yep. Would you say plus 1?
There we
Negative 1. Now, of course, you're going to have 2 fluorines to balance out, so we'll talk about that in a second. Alright, and then show the reaction between the calcium and the fluorine. I'm using the Lewis structures. Alright, Quentin, what you got?
Ca and dot dot. And then F, then 7 dots right next to it.
Okay.
Alright, so
Don't choke over there, you okay?
F right next to it and F under it. Well, no, like, right there.
go.
Can I just go there and draw it?
Draw it. Come draw it.
COVID.
I have to point at the ceiling, sorry, Jimmy.
COVID.
You're risking COVID for this?
Sure.
It's just my turn.
You have COVID.
I do not.
Are you both up?
I don't have symptoms.
Asymptomatic. Just like
Very creative done. Yes. Oh, it's the idea that this one is positive 2 because it's given 1 electron to this one and 1 electron to this one. So very nice and very creatively done. There's a couple different ways you could show that, but yes. I'm risking COVID too, but I just touched Quentin's shock, so I'm risking COVID. Alright, anyone have any questions about this? Alright. B. Which of the following compounds would you expect to contain an ionic bond? Remember, an ionic bond is between what type of substances, Chris?
Metallic and a non-metallic.
Good job. So a metal and a non-metal. So, which of these would you expect to have the most ionic character or the most far apart on the periodic table? So we'll talk about that in a second.
I put SO2.
Hang on a second. So, which ones of those would have an ionic bond? Ethan's turn though.
Gotta get his gerbil.
Excuse me. What? Sorry, I was.
Alright, which ones have ionic bonds on that list?
Oh, for 2A?
Yes.
CRI,
Good job.
LI, lithium oxygen,
Good job. Lithium oxide, so yes.
cesium fluoride,
Good job.
and calcium chloride too. Dichloride.
Good job. Alright, anyone have any questions about that? Alright, which one has the most ionic character or is the most farther or the most far apart thinking they're right? Alright. Chris?
CaCl2.
CaCl2? No.
CSF.
Good job. That one is the correct one because those two are the farthest apart. Alright, anyone have any questions about that? Alright, we're going to review at the end. So I don't have a whole lot of terms yet. I want to get through some stuff as
Jamie
well.
thinks this is whack.
No, hopefully not. Alright, so look over on page number, we talked about page 132. We're talking about covalent bonding. Alright, if we're talking about covalent, if we're talking about covalent bonding, what is this typically between, Quentin?
Covalent.
Covalent what?
Those
Metals for covalent bonding?
non-metals.
For covalent bonding? That didn't help you. What's the last thing? If it's not between a non-metal and a metal, or a metal and a metal, what's the last one? Who said metal and metal? Non-metal, non-metal, because remember they both want their electrons. So this is to represent your book. Tosh shows you at the top of the page between oxygen and hydrogen. So oxygen starts up with how many valence electrons?
6.
How many more does it need to be happy?
2.
2. How many does each hydrogen start off with? 1. So each hydrogen comes up and they bring their 1, and then oxygen I'm gonna color oxygen a little bit differently. Now keep in mind
Why does
again.
the hydrogen want 2 to be happy?
Okay, what is hydrogen? Because hydrogen is so small that hydrogen and helium, this one's a noble gas and it's satisfied with 2 valence. It also comes the octet rule as a general rule. They want 8 because all the others want 8. But sometimes the really small ones, they want the noble gas configuration of helium. So hydrogen, helium, lithium, and beryllium act like that they want this one's just 2 for it. So those are more of the exceptions. As a general rule, all the others want 8. Okay.
Oxygen is a non-metal and hydrogen is what?
Hydrogen's a non-metal too. So they both want to share. So oxygen brings over its 6. 1, 2, 3, 4, 5, 6. So oxygen shares one of its with the hydrogen and one of its other ones with the hydrogen. So each hydrogen has 2, and then I spaced them out weird. But the oxygen also has 8. So is everybody happy and satisfied? Ethan? Yes, they are. So the last bullet in your book at the top page is trying to show you is not as dramatic as the ionic one, but they're trying to show you how they will share their electrons. So again, not quite as dramatic as in the ionic one, but they're trying to show you that okay, that these 8 electrons on the outermost shell, that's why oxygen's happy, and then the hydrogen, because they just have 2 in their little circles, that's why they're happy. So that's an example of covalent bonding. Alright, anyone have any questions about this? Alright, so your book points out that these are typically between the nonmetals, and you can have a couple of different bonding types in this section as well for it. You can have a single, double, or a triple bond between the nonmetals, depending on how many electrons that they need to share to be happy. The first one it gives you is with carbon and with the 4 hydrogens, so methane technically. So it looks like this for it, because carbon starts off with how many electrons? Quentin? 4. So each electron, 1 around it, and then hydrogen brings how many? 1. So between that, each one has a single bond or 2 electrons. Kind of how, like, if you have 1 pair of socks, how many individual socks do you have? Chris? 2. So that's the idea. If you have a single bond, you have 2 electrons there. Alright, if you have a double bond, how many electrons do you think you have? What is that?
4.
4. What if you have a triple bond? How many is that then? Alright?
6.
6. If you have a quadruple bond, now quadruple bonds do not exist for real, but why? But how
8.
many would you have? You would have 8. Now keep in
8.
mind, why do you think we don't? We draw lines to represent the bonds as well. Why do you think we don't see carbon to carbon like this, where you have all of your electrons in the center? Anyone think about it? Why do you think we don't see this in nature?
Because God said so.
Okay, why?
God made it that way.
Why? Like
Because he
God
said
put laws in
that
nature
way.
that balance nature. Keep in mind, what's the charge of electrons? What's the charge of an electron?
Negative.
Negative. Do electrons like to be all next to each other?
No.
No, that's too much at that point. They don't like it, they're too clumped up, and they don't do that. As far as you can get is the triple bonds for them. So, your book points out an example of a double bond is between nitrogen and nitrogen, or if you have dinitrogen, because nitrogen starts with how many? Quentin. Does it actually draw a blank? Yeah, it starts with 5. So, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Alright, how many more does it need to be happy? 3. So because of that, we're going to color code again. This nitrogen, it'll put its 3, and that means it has how many left? Ethan, not being shared.
Not being shared.
Not being shared. So if it's sharing 3, how many is it not sharing? We start with 5. Alright, so if you have 3 apples, and if you have 5 apples, and you share 3 with Quentin, how many apples are yours alone? 2. Good job. Alright, so it has 2 that are not being shared, but 3 are being shared. Alright, if you have second nitrogen, alright, it'll come up and it'll share its 3, and then if it's sharing 3, how many is it not sharing?
2.
2. Alright, so because of that, I'm drawing. Be sure I'm in the right report. So for this one, I messed up somehow. What did I do that I messed up? No, I didn't. I'm sucking myself out. I'm okay. So because of that, I keep thinking I messed up, but I didn't. Okay, so how many electrons? So if these 2 are the shared zone, how many are right here, Quentin?
2.
Alright, and then how many is over here? So if this is the shared zone plus the 2, how many does this nitrogen have?
That's crazy.
8.
Easy count.
Alright, and then how many over here, Ethan? So if this is the shared zone, how many does this one have?
2.
And then if this is the non-shared zone, how many does it have total in?
2.
Alright, so the non-shared, plus 6 is
8.
8. So this one also has 8 as well. I was psyching myself out. For some reason, I was getting 12 when I was multiplying 2 by these by accident. So, yeah, so each one has 8. So, you have the shared zone in between them. Now, each of these electrons count twice. It counts for this side and for this side. So, that's part of the reason why you can have it form a triple bond like this. We have the 6 electrons. Typically, scientists, they don't draw them with dots because, as you can tell, it gets messy really quick. So, they'll start doing lines. The triple bond is represented by 3 lines. Single bonds are represented by 1 line. What do you think a double bond is represented with? Chris? 2 lines. Okay, anyone have any questions about that?
Can atom have 9 valence electrons?
It can actually. Your book's going to talk about one as an exception. It just typically doesn't, but it can. You okay? You okay? You alright?
9. On the test, but 9 for fluorine.
Oh, okay. Yeah, typically it won't though, but you can have these exceptions for it. Alright, so your book gives you actually one of the exceptions where it's talking about the polyatomic ions. Anyone remember from physical science what a polyatomic ion is?
Poly is multiple atoms.
Good job, that is actually it. So, polyatomic ion. Your book gives you the example of magnesium sulfate, so SO4, and magnesium. Yep, it's not magnesium. Alright, anyone remember what's the charge of this one?
Positive,
Okay, it's an anion.
negative,
Negative, what?
2.
Negative 2. So, this one has a negative. So, this one is covalently bonded. So, you have sulfur in the middle, and then you have the oxygens bonded around it. Sulfur starts off with how many electrons? Chris?
6.
You got 6, and then oxygen starts off with how many?
6.
6. So, whenever you work out on the covalent, you'll notice that, okay, sulfur, it does this to where it has double bonds, and then it has 2 single bonds. Well, sulfur, that means at that point that sulfur already has too many electrons, but then it'll also take 2 more because these oxygens want to be happy and satisfied as well. Because these oxygens want to have their 8 valence electrons, and they're basically forcing sulfur to have extra. Sulfur is one of the few that can have it. What?
Unconsensually? Like making them have it?
Yeah. Sulfur deals with it, but it's not super excited about it. But since oxygens are more electronegative, they want them more, they're basically forcing sulfur to deal with it. So again, this is one of the exception ones. You don't see this happening a lot, but I say the idea of it can. So just make a note though that most of them want to have the 8 valence electrons. Don't worry about if this one is an exception or not. You're not going to be asked in quizzes and tests which ones are exceptions and which ones aren't. This is one of the ones though. So this one is a covalent bonding, while this one is an ionic bond between the whole molecule because the magnesium gives its electrons to the sulfate, and so that's why the oxygens become satisfied. Alright, anyone have any questions though about that? It's just giving you an example of how you can have an atom that's made up of multiple atoms, that it can have both types on the inside. You can have the covalent bonding and then overall ionic bonding.
Can we review?
This class ends at 11, so not quite yet. Alright, anyone have any questions about this? Alright, so it also talks about you can have a covalent network. So your book points out generally covalent bonds hold atoms together in a discrete molecule or in a solid molecule. In some cases they will build up larger
It kidnaps them.
or what do you mean?
I said it keeps them in a discrete location. It kidnaps them.
Okay, it just means like it's in like a set spot for it, so don't get too distracted. So, some of them, they can build into a larger molecule of a covalent network. Basically, instead of them being locked into just these smaller units, they start growing and growing and growing. Kind of like a salt crystal or the ionic crystals, how they're the smallest ratio. This is the same idea, they just keep growing and growing and growing. So if I give you the example of the covalent networks, this one is a diamond. So a diamond has these 5 carbons bonded to a single other carbon, and it builds up pattern over and over and over again with the same basic shape. They're trying to show you a 3D structure, that's why it looks a little bit weird. They're trying to show you how it's basically 6 carbons bonded to each other over and over and over and over again, and it gets larger and larger and larger. Okay.
So I got a block of salt from a salt mine. Why does it ruin hardwood?
I don't know off the top of my head. I'm assuming, like you're talking just regular wood hardwood. I'm assuming because salt's a purifying agent that it's chemically reacting with the wood to break it
I
down.
think it pulls the moisture out.
Probably. That also would probably do it. Again, I don't know off the top of my head. I'm sorry. Alright, so make a note for it. And the diamond is the hardest known substance that has the carbon that is bonded together for it. Each covalent, so it's 1 carbon bonded to 4 others around it to build up the structure for it. Raise your hand. Raise your hand. What?
The only thing that can cut diamond is diamond, right?
For the natural occurring substance, I believe so. I think they've artificially produced substances that are stronger than diamonds now, but for a naturally occurring substance, a diamond can only be cut by another diamond. Alright, quartz is another example. Do you know where we get quartz from?
Another.
No. You get it from sand. So your book points out that this one is composed of silicon and oxygen atoms, and so it builds up the same structure over and over and over again. So just make a note though that diamonds and quartz, these are examples of a covalent network. Technically, you refer to the whole diamond as one single molecule of this type of carbon. That's the reason why diamonds, if you get a really large one, we call those macromolecules, because technically it's the whole thing is the whole molecule. We just refer to it as that simplest formula for it. What do we call the simplest ratio or the simplest formula? We talked about this with the ionic bonds.
Let's start with
E or F if you know the other word for it. It's that simplest repeating pattern.
energy.
Nope. Alright, empirical formula or the formula unit, either one for it. I think that's it for it. Does anyone know what the largest clear cut diamond is in the world today? It's still the largest
23 karat?
clear, what?
23 karat or something?
It's the, look at like largest, like it's a clear diamond
the
or a
one
white diamond because there's other colors
Is
of
it the
diamond.
one in maybe England or Britain?
Britain, yep,
Yeah,
it's
but
the
Queen
scepter one
Victoria-
on the
Queen
crown
Victoria?
jewel. What?
Was it Queen Victoria?
I think it was given to her. It's the one. It's the giant diamond on the end of like
On
the
the
scepter.
scepter?
Yeah,
How much would it
that's
cost?
They will not sell it today because it's part of their crown jewels. So it's like so it's like
That's
part of the
right.
British.
If it wasn't
Empire.
on there, probably like $1 million.
Not only is it the largest one.
Like if
But
it
it's
wasn't
also-
historically, it was just a really large, like it's just the biggest diamond ever.
There are a couple diamonds that are larger, but they're not clear. So I'm not sure, and some of them aren't cut either. That's like, oh, it's gonna, you have to get specific to say which ones are cut or chiseled, plus being the white ones. So it's the largest cut and the clearest one. So I don't know. I looked this up for Earth and Space Science last year. Some of them are like ridiculously expensive. It's like 9 million or above for some of them, based on their colors and like the
That's a lot of emeralds.
It's a lot. All right, anyone have any questions about this? Spin it out. So this is the
Sweet.
carbon example for it. For the covalent network, this is the quartz one. All right, no, we're not done. All right, metallic bonding. They're characterized by a sea of electrons. That's how your book describes them because nobody wants them. So these have a tendency to be between metals because remember metals, which is how many valence electrons do most metals typically have?
Two.
One.
Yeah, 1 or 2 for it. And so because of that, which is easier, lose 1 or 2 or gain 6 or 7?
Who's one?
Lose 1 or 2. And so because of that, they all go, I don't want it. And they throw them out onto each other, but nobody else wants them, so they keep throwing them out to each other. So these constant electrons are constantly being reshuffled around. Nobody wants the electrons. Now, since nobody wants them, they're not locked in, so they are delocalized. So
I feel
you
like
think,
an
wait,
electron.
raise your hand. What is it?
I feel like a delocalized one.
Okay, don't get too distracted. I know you've made that joke several times, but don't get too distracted because I have to go.
Great.
But it's the idea of they're not local, they're not locked in, nobody wants them. So they're getting pushed out constantly into this sea of electrons. Now, keep in mind though, if you have the metals get rid of their electrons, what charges are they going to have? Positive. If they're going to the side, the reason why the electrons don't just fly off is because the electrons are still negative. So it's because they're still attracted to them, so they can't leave, but they can't be locked in either. Alright, the book points out there are several properties that contribute to this to give metals their distinctive properties. Let's go through that kind of list at the top of the page. So page 133 gives you these bullet points at the top for it. This is a characteristic of metals, and it's the reason because of this metallic bonding. Alright, Quentin, why don't you read that first bullet point at the top of the page?
They're good conductors of electricity.
Why do you think that is? Why are they good conductors of electricity?
There's a metal.
Why? Okay, think about it with metallic bonding. Like, why are metals associated for being a good conductor of electricity?
Because they don't want any extra electrons.
So, for metal, like for this one, I believe this is aluminum, that if I were to hook up electricity to it, electricity is made up of what? Do you know? We haven't talked about this class. Okay.
Energy.
Technically, it's a
Light.
type of energy. Nope.
Plasma.
Nope. It's made up of extra electrons, basically. Electricity is electrons moving. So if I were to hook on extra electrons, the metal still doesn't want it. So the electrons are able to all shift down together. And if I hook up another end, like another wire to connect it, the electrons will go through the wire. This is one reason why, if you take a piece of metal and shove it into a socket, the metal,
It hurts.
yeah, it does. The metal, once it touches the socket on the inside of it and it connects, because electricity is going through your house constantly. That's how come you don't just shove metal and stuff all the time. Because if you do it, you're not connecting another pathway for the
I've
electrons
tried
to
it, it
flow.
hurts.
Nope, raise your hand. This is because it's connecting another pathway for the electrons to go on. That's the reason why the electrons, they don't want to stay on the metal though, because the metal doesn't want them. So it'll flow up the knife or whatever it is into your hand and then down into the ground. That's what sometimes stings and you might even get burned depending on how much it was. Okay.
Yeah, I've done it with a fork, it hurts. Also, shouldn't you say like don't try this at home?
Yeah, disclaimer, don't try this at home on YouTube. Okay.
Isn't that how chargers work?
Chargers? That's probably the reason
The
why.
metal on the bottom, it goes up the cords into the phone and
Yeah.
charges it.
So, like, for this is why, this is also why you don't plug it in slowly. If you've ever done that, you'll notice there's sometimes a spark that comes off of it. It's because because the closer you get to it, sometimes the electrons will start to jump from the metal on the inside of the socket to the metal because they can sense it. That's the reason why you don't like half plug it in and half plug it out. That's why it starts to spark whenever you do that, because it's jumping from one into the other.
Shocked myself when I was plugging in a charger the other day.
That's probably
It felt weird. I was
probably part of the reason
I was,
why.
I was thinking with my own body when I was like, I don't
Yeah.
know if that was supposed to happen.
Yeah, so it's one of those, it's not supposed to happen for it, but if it happens, you'll probably be fine, but if it's too much, you could get burns from it. Alright, so good conductors of heat. Alright, that also has to do with the idea because the electrons aren't locked in, the heat or that vibrational energy is able to travel through it quicker. There's one reason why you don't leave a hot object on the stove, and that's part of the reason why your utensils for stirring things on the stove are typically made of a special type of plastic or a special type of wood. Typically you don't use metal spoons in the stove. If you do, you don't leave it in the pan while you're cooking. If your mom probably yells at you if you do that because you're not supposed to do it, because the metal and the spoon will also get hot. Alright, so let's look at the next one. Who wants to read that one?
Okay.
Alright, Chris.
They're malleable.
Aaron?
Meaning they can be hammered into shapes, and ductile, meaning that they can be drawn into wires.
Good job. So, ductile with the idea that they can be drawn into thin wires, and then malleable. There's one reason why if you ever watched craftsmen like make swords or make an object and they're hitting it over and over again, that's the reason why. They're bending it into that particular shape. Alright, the next thing is what, Ethan?
I'm trying to remember that.
Okay, top thing 133 and the little bullet points at the top.
Shiny and high resolution.
Yep, and then also they have very high melting and boiling points. Your book gives you the explanations on the next page for it. So flip over to the next page. That unlike the tightly bound electrons of covalent bonds, that these they're able to be reflective of. That's part of the reason why metals look kind of shiny to us. Now, depending on the type of metal, they might have more luster than others. Other than why they look shiny to us because they're bouncing the light off of them for it. So metal can absorb and emit a wide range of wavelengths. This also accounts for metal's luster and makes them highly reactive with a highly reflective. Sorry. Alright, your book has this diagram at the top trying to show you how it works for an object to be malleable. So it showed you, okay, here's a metal, because the cation of the metals, all of them are attracted to the negative electrons. So if you hit it, they're all able to just shift down easily because they're not locked into place. If you have a covalent or a ionic bond and you do that, because they have this pattern, if you try to shift them, they don't like that. And so because of that, you're going to have it shatter or break. So that's what it's showing you. If you try to shift, they won't do it right. What is it, Ethan?
Glass.
Yeah, glass is a type of amorphous solid. That's probably the reason why for it. Now keep in mind, if you heat up glass first, you can use glass blowing, and you can blow it that way. But this is one reason why typically they will break for stuff like this. Alright, anyone have any questions about that? Alright.
Review.
I can't get anywhere in the next 10 minutes. Alright, so thinking back over overview, what game do y'all want to play since the last time?
Darts.
Wanna play darts? Okay. Sorry, Damon.
Those were being asked.
Yeet. Yeet. Alright, so thinking back over it, that's not y'all. I'm sorry. Thinking back over it, what type of bond is between a non-metal and a non-metal?
Let's start with D.
Ionic, covalent, or metallic?
Covalent.
Non-metal is non-metal.
Covalent.
Covalent is correct. Let's put it up the ceiling. Sorry, Jamie.
Nice.
Right here.
That's it. Ooh, look at a minute.
5. 9.
Alright, it's on the line, so 5 a rethrow, and then that one's also on the line.
I'm rethrowing both of them.
Alright. between a non-metal, no, I already asked that, between a metal to a metal. Whichever one.
Metallic.
Metallic. Did you touch your face?
What face?
The one you don't have.
Yeah, I hope I don't have yours. I wanna look at it.
I hope I don't have yours.
Alright, come through. Watch out for my poor presidents.
How can you play basketball with that kind of accuracy?
Alright, that's more on 11. Right?
the best
Chris
player
also
ever.
touched your face, so.
I'm not touching my face, man.
Why are you saying it? You didn't answer my question yet. What do you call, what type of bond is it between a non-metal and a metal?
What is?
Okay, not too hard, don't hit my board.
How can you play basketball with that kind of accuracy?
I'm not starting.
Alright, what if you share, so if you are covalent bonding and you're sharing 2 electrons, what do we call that? Come away from Ted, leave the man alone.
dude.
Alright,
Is that a guy or is he
There's a guy, girl.
I actually don't remember. I think it's a male, but I don't remember what we specifically picked.
What's the girl?
Double one.
You're a citizen.
If you're sharing 2 electrons,
Single one.
single bond.
That would be Teddy if it's a girl.
You can change it, ready to go.
It's a girl, Teddy. That's a 0. That's 11.
That's 11. It's close enough on the line. I'll let you reverse.
Throw both of them?
No.
That's what I'd say.
Where's this?
11.
Right here.
Brick. 5. That's fine.
Alright, Ethan. Careful to touch your face. Alright, what do you call if you're sharing 4 electrons? How many, let's see, what do you call that to bond? Put it away! It's still my time, Chris. Put it away.
Double.
Bro, put it away. It's still my time. You can write the terms on the back if you want to, but put it away. Alright, if it is a triple bond, how many electrons are you sharing?
Wait, no, what?
Triple bond.
6.
6. Come through. Alright, which one is characterized by a sea of electrons?
You have metal in your ear, right?
That one don't.
Where's over?
Ionic, covalent, or metallic?
Metallic.
Which one?
Metallic.
Metallic. Nobody wants them.
Don't brick, man. Don't brick.
Have you seen this man shoot threes? He never breaks. He always has balls.
Alright, what type of bond is characterized by the exchanging or transferring of electrons? It starts with, what type of bond? Ionic, covalent, metallic, with the transferring of electrons. Ionic, good job. One of them's giving away, another one's taking it.
Covalent.
Wait for my question.
With.
Alright, what is the rule that says they tend to want to get noble gas configuration, which is typically 8?
Octet rule?
Octet rule.
There's an L in it.
O-C-T-E-T? There's no L in that. 15, hey. Alright, Quentin's turn. Alright, Quentin. So, if it's between, that's still not going. Alright, what do you call it whenever you have billions or trillions of atoms that are bound together to a single unit by by covalent bond? Bring them back, Chris.
So what is it?
So like a diamond and a quartz, what do we call that?
This over.
C.
Took the whole can't do that.
Grab it. I would not trust it. Alright, permission to raise your hand? Go.
What's the question?
No.
Can you no what? Say the question one more
Should
time.
have been paying attention
Please,
to the
please. I would no. I was putting the stuff back.
No.
No,
Covalent
no.
Network.
I'm going to eat it.
Covalent.
Covalent network.
Moldova.
Don't sit in the corner.
Sit down.
Can I stand beside my desk?
You can. for an example, if you have a molecule that is this, what type of bonding is this?
I don't know what those two are.
Lithium bromide. I'm gonna write it up in the top so Jamie can see it.
It's like, I don't even know where those are on the board.
Find them. Lithium bromide. There you go, Jamie. You can see that.
There's a nail where you are.
Yes, it does actually.
Not really.
Where's lithium? Where is lithium?
It's in group 2, I believe.
1.
1.
Okay, then it's ionic.
Ionic
I'm
bond.
still trying to figure out what BR is. There it is.
Found one out.
Group 17. Alright, point is, if it's this, what type of bond is that?
Depressing.
Nope. Good luck.
Oh. What's NI?
Ni is nickel, so it's copper and nickel.
Metallic.
Metallic.
Nico. Alright, come on, Naruto.
I think y'all wrote this one.
Quentin. 10.
Alright, what type of bonding is it here? If it's sulfur and oxygen.
Valid.
It's sulfur and oxygen?
Covalent.
Covalent, because they're both nonmetals.
This is why your dad is a barbecue shop.
Okay.
I'm sorry, you said.
You ever feel like a dart?
No, I feel like a paper bag thrown through the wind.
Alright,
Paper here, 2016.
alright, so what is this substance? What type of bonding is that?
19 was trivia.
Is it?
No. Covalent.
Covalent, because they're both nonmetals.
What was that? It was.
No threatening people.
I'm looking at it very innocent.
Alright, we'll probably be at the last one. So what type of bonding is it between metals? Metallic? Okay, that's y'all.
No, I was just
Sit down.
Alright, what's my question?
What type of bond is it between a nonmetal and a metal? Good job. So metal to, so non-metal to non-metal is? Chris?
Non-metals is covalent.
Covalent. Okay, wait your turn.
Y'all get out of the way.
Move.
Wait,
I took them.
Alright, Chris, turn. The back is probably there. Don't watch out for Ethan. Alright, out of your points.
What was it?
Who got 50 or more? Because some of you had some high numbers.
Hey.
Alright, who got 75 or more?
Board twice.
Alright, who
Hold on.
got 80 or more?
I hit the board twice.
Alright,
Does that count?
90 or more? Alright, Ethan, did you get 80 or more?
I had 85.
Oh, did you have?
80.
Alright, Ethan wins over, get your candy. Alright, you
Was
can
that
watch
6 seconds?
You can't
What?
watch yet.
I
You
had
have
79.
5
already
seconds.
did it.
I had 79 and I got that 6.
You have 10 seconds. Wait,
Really?
yeah.
Did you turn the recording off?
What?
Did you turn the recording off?